In engineering and physics, we often need to find the total mass of a thin plate, called a lamina. If the material is uniform, mass is simple to find, but what happens when the density changes across the surface? In many real-world objects, the material composition isn't uniform. We represent this using a density function, ρ of x and y, which tells us the mass per unit area at any specific coordinate on the plate. To find the total mass, we must sum up the mass of every tiny piece of the lamina. Each infinitesimal piece has an area dA and a mass dm, calculated by multiplying the local density by that tiny area. Before calculating, we must define the boundaries of our lamina. We typically describe the region D using inequalities for x and y, which become the limits of our iterated integral, usually starting with the inner variable. If the lamina is a rectangle, our limits are simple constants. However, for general shapes, the inner limits will often be functions of the outer variable, requiring careful setup to cover the entire geometry correctly. You can visualize mass as the volume under the density surface. Just as the integral of a height function gives volume, the integral of a density function over a 2D area gives the total mass. Let's calculate the mass of a triangular lamina bounded by y equals 0, x equals 1, and y equals x, with a density function ρ equals x times y. First, we identify our limits x goes from 0 to 1, and y goes from 0 to x. We set up our iterated integral. We integrate the density function xy with respect to y first, treating x as a constant. This accounts for the vertical strips across our triangular region. Integrating xy with respect to y gives us x times y squared over 2. Evaluating this from 0 to x, we substitute the upper limit to get x cubed over 2. The lower limit of 0 leaves us with nothing to subtract. Now we perform the outer integration with respect to x. The integral of x cubed over 2 is x to the 4th over 8. Evaluating from 0 to 1, we find the total mass of the lamina is exactly 1/8. For circular shapes, Cartesian coordinates can be difficult. If we have a disk with density proportional to the distance from the center, switching to polar coordinates makes the integration much simpler and more elegant. In polar coordinates, x squared plus y squared equals r squared, so our density becomes simply r. Don't forget the Jacobian factor rt in the area element dA, making our integrand r squared. Our limits for a full circle of radius 2r are from 0 to 2, and theta from 0 to 2 pi. We integrate r squared with respect to r first, which gives us r cubed over 3. Evaluating the inner integral gives 8/3. Integrating 8/3 with respect to theta over a full circle multiplies the result by 2 pi, resulting in a total mass of 16 pi over 3. To recap, always start by sketching the region to find your limits. Choose between Cartesian or polar coordinates based on the shape, set up your iterated integral, and solve from the inside out. Here is a quick question: if the density is a constant k, what is the relationship between mass and area? As you can see, the constant pulls out of the integral, leaving the density times the total area. Calculating mass is the first step toward finding the center of mass and moments of inertia, which are critical for understanding how objects balance and rotate in engineering design. You now have the tools to calculate the mass of any 2D lamina using double integrals. Practice with different regions and density functions to sharpen your skills. Generated by Vision Solve AI.